Shall we go? According to figure 1, find the velocity at times t equals 10 seconds and t equals 20 seconds. And also the distance traveled in the first 20 seconds. Okay? At 10 seconds, we have, note that we have a graph here of acceleration versus time. Okay? And the relationship that you should know is that the acceleration is equal to the derivative of the velocity with respect to time, v being a function of t, as is a. Or we can also look at things in terms of the velocity being the integral of the acceleration, which is a function of time. Okay. So, in this case, stop just a moment. Notice that they failed to provide the initial velocity. So, we will be forced to assume that the object began with 0 velocity. And that will be not too great of a restriction here. Okay, so to find the velocity, we need to look at what the initial velocity was. Let's start out with a graph of velocity versus time. So let me pull this down here and see if I can. I'm going to actually graph it on top of here. The red values will be velocity measured in units of meters per second. Okay? So notice that we have an initial acceleration of 2 meters per second squared. Okay? And therefore, we will need a new set of units. For the red numbers, this will be 10, this will be 20, this will be minus 10, minus 20, minus 30. And you could do this on a separate graph, but I want the time scale to remain the same. Since the acceleration is the slope of the velocity versus time graph, we know that the slope of the line beginning here at 0 will be 2 because the acceleration is 2 meters per second squared. So in the duration of 5 seconds, the velocity will increase to 10, and this is very convenient that it goes up to here. The velocity will increase by 10 meters per second over, excuse me, that's, yes, okay. And over the course of 10 seconds, the velocity will go from 0 up to 20 meters per second. And the slope of this line here is 20 over 10, which is 2 meters per second squared. Okay? From 10 seconds until 15 seconds, notice that the acceleration is 0, which means the velocity is not changing. Therefore, on our graph, velocity would remain constant for those 5 seconds. From 15 seconds to 20 seconds, notice that the acceleration is negative 3 meters per second squared. So each second, the velocity will decrease by 3 meters per second. So in 5 seconds, the velocity will decrease by 5 times 3, which is 15 meters per second squared. Meters per second, excuse me. So that at the end of the 20 seconds, the value here will be 5 meters per second. Now if we go back, the first question was, what is the velocity at t equals 10 seconds? And remember, that was 20 meters per second. at t equals 10 seconds. And here, during the 5 seconds, it remained at 20 meters per second, and then at the during the final 5 seconds, again, it dropped by 15 meters per second, and so we ended up with 5 meters per second at 20 seconds. Okay, so that's the answer to the first two questions. We also need to know the distance traveled in the first 20 seconds. Okay, so notice that this shape we have here, what you need to realize is that distance is equal to the integral of velocity with respect to time, dt. Or that similarly, you can write that the velocity as a function of time is equal to the derivative of the position, let's call that x, with respect to t. And of course, x is also a function of time. Therefore, the distance is simply the area under the curve. The change in distance, the displacement, is this area. Well, let's continue that down here. Okay. So that area is what we need to calculate, and we can find it most easily if we break it into 3 geometric parts. We have a triangle to the left. We have a triangle here, we have a rectangle, and then we have a trapezoid. Okay? And for the triangle, we'll calculate the area here, and pay attention to the units here. We'll have 1/2, again, we'll have 1/2 the base times the height. So for the, let me mark this, area of the triangle is equal to 1/2 the base, which is 10 seconds, times the height, which is 20 meters per second. Notice that when we multiply this out, we get 1/2 of 200, which is 100. And notice the units of seconds cancel, so we get a unit of meters, which is what our distance should be there. The area of the rectangle is going to be equal to the width of the base times the height, so that is 5 seconds, times the height, which is again 20 meters per second. So during those 5 seconds, the object moved an additional 100 meters. And finally, the area of the trapezoid, and I'll put, let me call it TR, okay, is equal to the width of the base, 5 seconds again, times the average height, which would be, it begins at 20 meters per second, and it goes down to 5 meters per second. Again, although my drawing does not reveal that so clearly, that is a straight line. That red line should be a straight line. That's why this is a trapezoid. Divide that by 2. Okay? So that the average of 20 and 5, 25 divided by 2 would be 12.5 times the 5. And so that one we may need to double check with the calculator to get it exact. 12.5, 62.5 meters. Okay. And so the total distance that was traveled is equal to the total of those three, which would be 262.5 meters. Okay.